Dear students, I am Anuradha Rajesh welcoming you to today's learning journey. We have already been made familiar with terms like work, energy and power in class 9. In our everyday life too, we have been using these terms very frequently. A laborer carrying a load of bricks, a student studying for long hours, or a farmer ploughing his fields are all considered to be doing work. However, in physics, work covers a definite and precise meaning. Somebody having the capacity to run for several miles is supposedly having a large stamina or energy. In physics too, the term energy is related to the capacity of doing work. Students, we often talk about powerful punches delivered at a great speed by a boxer. This shade of meaning is close to the meaning of the term power used in physics. In fact, there is a loose correlation between the physical definitions and the physiological pictures that these terms create in our minds. In this lesson, we will develop an understanding of the three physical quantities: work, energy and power. After today's session, you will be able to explain the meaning of work in scientific terms, calculate the work done by a constant force or by a variable force, establish a relationship between work and energy in the form of work-energy theorem, distinguish between conservative and non-conservative forces, define gravitational potential energy. So, what is the precise meaning of work, or when do we say that work is done? Let us consider a constant force acting on an object at an angle theta. So, here we are considering an object having mass m, say, and being acted upon by a force F, which is acting at an angle theta with the horizontal. The force is leading to a displacement d in the direction as shown. The angle between the force and the displacement in this case is theta. In order to calculate the work, we would need to find out the component of force which is acting along the direction of the displacement. This component of force will be given by F cos theta. The work done can be found by multiplying the component of force acting along the direction of displacement and the displacement. Therefore, the work done will be given by F cos theta into d. Therefore, W is equal to Fd cos theta. This can be represented in the form of dot product of the vectors force and displacement as F dot d. So, here we have calculated the work done by a constant force. The SI unit of work done is joule or Newton meter. There are other units of work done as well, like ergs, electron volt, kilowatt hour. The dimensional formula of work done can be easily calculated by you all. It is m L square T power minus 2. The work done is a scalar quantity. It can be positive, negative or 0. We see that if there is no displacement, there is no work done even if the force is large. That is the reason that when you push hard against a rigid brick wall, the force you exert on the wall does no work. Thus, the meaning of work in physics is different from its usage in everyday language. Let us try to understand the nature of the work done. We now know that the work done is represented by W is equal to Fd cos theta. Clearly, work done is positive when the value of cos theta is positive. That is, when theta lies between 0 and 90 degrees. For example, a car engine driving the vehicle forward certainly would do positive work on it. The work done by the force of gravity on a freely falling object will also be positive. Work done will be negative when cos theta is negative. That is, theta is more than 90 but less than 180 degrees. An example of negative work done would be the application of brakes to a vehicle. In such a case, the force opposing the direction of motion comes into play. Therefore, theta is 180 degrees and therefore, the work done is negative because cos theta is minus 1. Similarly, the work done by frictional force on a moving object is also negative. Work done could be 0 in 3 different cases. The first one, when force is 0. Dear students, you may be thinking that if force is 0, the displacement would also be 0. Well, that's not at all necessary. According to first law of motion, no force is required to keep an object moving with constant velocity on a frictionless surface. Such an object may undergo large displacement without any work being done on it. This situation is, however, far from realization because friction always comes into play. The second case for work done to be 0 is when the displacement is 0. A weightlifter holding 150 kg mass steadily on his shoulder for 30 seconds does no work on the load during this time because his displacement is 0. The third case for work done to be 0 is an interesting one because here neither the force nor the displacement are 0. In fact, they are mutually perpendicular to each other. That means theta is equal to 90 degrees and the value of cos theta, that is cos 90, is 0. If we assume that the moon's orbit around the earth to be perfectly circular, then the earth's gravitational force does no work. The moon's instantaneous displacement will be tangential. You could see here, suppose I am considering this to be the earth and the moon over here. The instantaneous displacement can be found by finding a tangent by making a tangent, and the direction of force is along the center. Since the tangent is perpendicular to the radius, the value of cos theta would be 90 degree. Thus, the gravitational force does no work in making the moon move around its orbit. Another very common example of 0 work done is considered to be a coolie walking on a horizontal platform with a load on his head. In this case, no work is done by the coolie against the force of gravitation because it acts perpendicular to the displacement. However, it is to be noted that the coolie does work in overcoming the force of friction which acts in a direction opposite to his motion. So, dear students, I hope that now you have understood positive, negative and 0 work done. In our previous discussion, we had considered the force to be a constant. However, a constant force is rare. It is the variable force which is more commonly encountered. Let us try finding the work done by a variable force. This graph shows a variable force Fx. Here we have taken, in the graph we have taken displacement along the x-axis and the force along the y-axis. If we consider a small displacement delta x, as here, for which the force Fx could be almost considered to be a constant, then the work done in this particular small displacement, you could see this is the small displacement, and the value of force can be almost considered to be a constant. So, in such a case, the small amount of work done can be found by multiplying the force with the delta x, which is the small displacement. This Fx delta x represents the area of the rectangle which is here shown shaded. Total work done by the force can thus be calculated by taking the sum of successive rectangular areas. Therefore, the total work done W can be found by summing up the product of Fx delta x starting from an initial position xi to a final position xf. If we consider the small displacement delta x to approach 0, then the number of terms in the sum increases without limit, but the sum approaches a definite value which is given by the area under the curve. Thus, it is possible for us to replace the summation sign by an integral sign. So, here we have made an integral sign and w will be given by integral xi to xf fx dx. Hence, we see that the work done by a variable force can be expressed as a definite integral of force over displacement. If we try to understand this using the graph, the definite integral of force over displacement is nothing but the area under this particular graph between xi and xf. After learning the precise scientific meaning of work done, let us now discuss about the next physical quantity, energy. Energy is defined as the capacity to do work. So, in order to do work, one needs energy, or work is done at the expense of energy. Work and energy are related to each other using the work-energy theorem. According to this theorem, work done by a force acting on a body is equal to the change produced in the kinetic energy of the body. So, let us consider an object moving along the x-axis under the influence of a variable force Fx. We know that the kinetic energy possessed by a body is given by half mv square. If we find the time rate of change of kinetic energy, it will be dk by dt to be equal to d by dt of half mv square. Half m could be taken out and what would be left is d by dt of v square, which will be equal to 2v dv by dt. Hence, we have dk by dt to be equal to m dv by dt into v. 2 will get cancelled. Now, dv by dt here can be represented as acceleration of the body. So, this will be equal to m into a into v. ma can be written as the force acting on the object. Therefore, we can say that the time rate of change of kinetic energy is nothing but equal to force times velocity. Velocity, however, is the time rate of change of displacement of the object. Therefore, dk by dt, which is the time rate of change of kinetic energy, is equal to f dx by dt. If we cancel out dt, what we get is that the change in the kinetic energy is equal to f dx. Integrating both sides, applying limits, we will have integral of dk from an initial kinetic energy to a final kinetic energy. This will give us the total change in the kinetic energy to be equal to integral xi to xf f dx. Now, xi and xf here represent the initial and the final displacement. Therefore, we have the change in the kinetic energy to be equal to integral xi to xf f dx. Just now we have found the work done by a variable force, and we know that the work done by a variable force is nothing but integral xi to xf f dx. Hence, we have now proved that the change in the kinetic energy is nothing but equal to the work done. Thus, the work energy theorem for a variable force has been proved. So, we have now established a relationship between work and energy and showed that work done is equal to the change in the kinetic energy of a moving object. At this point, it becomes important for us to understand the concept of conservative and non-conservative forces. A force is said to be conservative if the work done by the force in moving a body between 2 points is independent of the path followed. Let us consider the work done against the gravity in the following cases. In this first case, let us consider an object of mass m being lifted to a height h without any acceleration. The force which will be acting here will be mg, and the height or the displacement through which the object has been taken will be h. Therefore, the work done, which is equal to the force into displacement, can easily be found out by as mgh. Now, let us move on to the second case, wherein the object of having mass m is taken to a height h through a series of steps having heights, say h1, h2 and h3, the total height being h. Let us now calculate the amount of work done against the force of gravity. In this case, in taking mass m from say A to point C would be m g h1. This will be say W1. For taking the object from this point to this point, we could see that the displacement is acting along the horizontal direction, whereas the gravitational force would be acting along a direction perpendicular. Therefore, the angle will be 90 degree and hence no work will be done against the force of gravity to move an object along this particular path. Again, from going from here till here, we will require work to be done, which will be given by mgh2. Again, along this path, no work will be done because the angle between the force of gravity and the displacement will be 90 degree. Therefore, the work done now W3 from here till here, therefore, will be given by mgh3. The total work done will be the sum of all these three, which will be given by W equal to mg into h1 plus h2 plus h3, given as nothing but mgh. So, you could see whether I take the object straight up or through a series of steps, the work done against the force of gravity remains the same. In our third case, we will take the mass m through an inclined slope to a height h. For doing this, we will have to apply a force equal to mg sin theta. It is to be noted that here also we are considering the object to be moved without any acceleration. The displacement through which the object would move is given by L. Hence, the work done can be given to be equal to mg sin theta, which is the force, into L. If we consider this triangle wherein the inclined plane is making an angle theta, then sin theta will be given by opposite side upon the hypotenuse, which is h upon L. Therefore, we can replace sin theta by h upon L. What we get as a result is again mgh. Therefore, we have now proved that whatever be the path through which the mass has been raised to a height h, the amount of work done against the force of gravity remains the same and it is equal to m into g into h. So, now we know that gravitational force is a conservative force. Forces like electrostatic force and magnetic force are also conservative in nature. These forces are often referred to as central forces because they act along the line joining the two interacting bodies. On the other hand, if the work done by a force in moving a body over a closed path is non-zero, or the work done is dependent on the path taken, then the force is said to be a non-conservative force. The work done by the force of friction in moving an object from a point A to point B will be dependent on the path taken. Force of friction therefore is considered to be a non-conservative force. Let us now learn about potential energy in detail. The word potential suggests possibility or capacity for action. The term potential energy brings to one's mind stored energy. In fact, potential energy is the stored energy by virtue of the position or configuration of a body. Potential energy is of different types like gravitational potential energy, elastic potential energy, electrostatic potential energy, or even magnetic potential energy. The units and dimensions of potential energy are the same as that of work or energy. Let us try to formulate and understand gravitational potential energy. Here, we may consider an object raised to a height h above the ground against the force of gravity. So, here. The work done in doing so will be given by force into displacement, which is m into g into h, which is mgh. Therefore, the work which is done in lifting the body from this position to this position through a height h is stored in the object in the form of potential energy, and this potential energy is the gravitational potential energy. If h is taken as a variable, it can easily be proved that the gravitational force F equals the negative of the derivative of Vh, which is the potential energy. This turns out to be minus mg. Minus sign here indicates the fact that the gravitational force is acting in a direction opposite to the displacement. Here, it is worth noting that mgh represents the change in the gravitational potential energy and not the absolute value of the potential energy. Let me explain this to you with an example. Let us consider an object placed on the table. Suppose it has a potential energy of say 500 joules, and then we raise the object to a height h. If the potential energy now is say 650 joules, how much work is done to raise the object? Clearly, it is 150 joules, that is 650 minus 500. This will be equal to mgh. So, mgh basically is representing the change in the gravitational potential energy and not the absolute value. It is to be noted that this potential energy is the negative of the work done by the gravitational force in raising the object to a height h. If h is taken as a variable, of course, we have already seen that minus d by dh will be equal to minus of mg. When the body is released, the stored energy releases in the form of kinetic energy. I can give you an example. Let us consider a stretched bowstring storing elastic potential energy. When it is released, the energy is converted into kinetic energy. Another example could be the compression or extension of a spring. We shall be discussing the potential energy of spring in detail in our forthcoming sessions. Till then, learn and revise the concepts learnt and try to solve questions relating to the topics discussed from your textbook. Meet you all in the next session. Thank you.